this. But continuing on with the ammonium test, we're going to convert the ammonium to ammonia. And then we're going to drive off the ammonia as a gas. And another property of ammonia, well, ammonium is an acid. Ammonia is a base. And there aren't that many bases, though actually there are a lot of bases, but there aren't that many gases that are also bases. When we think about CO2, CO2 is an acidic gas. Nitrogen's neutral, oxygen's neutral. Pretty much, this is it in molecules that are similar to this. And so what we're going to do is we're going to test the gas. So we're going to cover this with a watch glass, which is going to trap the gas. And so in here we have our, there's going to be hydroxide in here. We're going to put in excess hydroxide. And then we should generate ammonia gas here, NH3 gas. The way we're going to detect the presence of this gas is we're going to stick a piece of red litmus paper on the bottom of a watch glass, this cover. And so as the gas rises, it'll strike the red litmus and turn it blue. We got to make sure it's the gas that's touching the litmus and not the hydroxide. So we're going to stick it on the bottom of the watch glass, but how do you get it to stick? The way we're going to get it to stick is we're just going to wet it. And so a wet piece of paper should stick to the bottom of the glass. And so what should happen here is the gas should rise up and it should react with the red litmus. Red litmus is actually an acid, and so I'm going to call it H-lit. And then what's going to happen is an acid-base reaction. The H-lit is going to lose a hydrogen ion to ammonia, forming ammonium, and we're going to be left with litmus minus, the litmus anion, which is kind of a big organic anion. So I'm not going to write out the whole formula for it. But this is it. And so if we get a gradual change from red litmus to blue litmus, then what we can say is that this is going to be a positive test for ammonium ion. We had ammonium present. But ammonium is not the only ion that likes hydroxide. Silver also likes hydroxide. But when silver reacts with hydroxide, what we form is silver hydroxide. Silver hydroxide turns out not to be the most stable of precipitates, and this silver hydroxide, if we have two of those can undergo further reaction to form silver oxide, which is much more stable. Silver oxide and water. And so we end up with a black PPT here. So we might see a black PPT if there's silver ion present. If there's lead ion present, then we should see a white PPT. Lead 2 hydroxide is a white PPT. If there's barium present, does barium precipitate with hydroxide? Hydroxides are all insoluble except for group 1, ammonium. Not that one. It would be group 1, ammonium, and calcium, strontium, and barium. So barium with the 2 hydroxides, there's no reaction here in our. Manganese likes hydroxide, and we end up with a brown precipitate. Well, it turns out in our known solution, all of these are present. So what we're going to get is we're going to get a black, white, and brown precipitate all mixed together. When you mix a black, white, and brown precipitate, it just comes out brown. And so a mixture of precipitates are going to form in this. But that's not going to interfere because these precipitates are solid. What we're testing is the gas rising off this. We don't necessarily need heat. We could just swirl it or agitate the solution to try to drive off the gas. You know, that's one. So let's take a look at what the procedure says to do. We look at the procedure for identification of ammonium. It's just detecting the presence of ammonium ion. So this is the only cation tested with a separate sample of solution. We're going to need 3 milliliters of mixture for this test. And so you can measure out about 3 milliliters. And then we're going to need about 3 milliliters of sodium hydroxide. We don't have to measure that so precisely. The sodium hydroxide, if you use those plastic dropper pipettes, you know, one full squeeze of the plastic dropper pipette is about a milliliter. Or about 20 drops is a milliliter. So we could just guesstimate that. In fact, the amounts don't have to be so precise, you know, because we constantly adjust the amounts depending on what's happening. But anyway, that should be adequate for this. So we're going to convert the ammonium to ammonia using hydroxide. And so ammonium gets converted to ammonia. And then we're going to drive off the ammonia as a gas. And we're going to either heat it gently to drive it off as a gas or just swirl it or agitate it. And so what do they say to do here? Quickly cover the watch glass to trap the ammonia. Swirl gently, taking care not to splash the litmus. So they're just saying agitate the solution to drive off the ammonia. And we want to cover it with a watch glass so we trap the ammonia so the ammonia doesn't escape out of here. And also we don't want to splash the litmus paper because the litmus paper is sensitive to base and there's lots of base hydroxide in the liquid here. And so that would also turn it blue. There are going to be some other reactions, side reactions going on. The silver likes hydroxide, forms silver oxide and water. The lead likes hydroxide, forms lead 2 hydroxide, and manganese 2 likes hydroxide, forming manganese 2 hydroxide. So we get the black, white, and brown precipitates here. Okay, so these precipitates will give you a clue as to what else is in there. We have all these in there. All right, that's the test for ammonium. We're going to use 3 milliliters of known standard solution. This is the known standard. You're going to have more than 3 milliliters. You're going to need more than 3 milliliters because we're going to go to the next series of tests. Here, not the anions. We're going to do the anions at the end. We're going to test for the remaining cations. Now the test for the remaining cations is going to occur on one 12 milliliter sample. And so ammonium, we wasted 3 milliliters of our known standard to test for ammonium. We got to make sure we have at least 12 milliliters to test for the remaining. Now we aren't going to do individual tests here. We're going to take advantage of chemical properties. We're going to take advantage of chemical properties of silver, lead, barium, and manganese in order to separate those from each other and then test for them individually. And so we're going to go through this analysis step by step here and take a look at all the reactions that are happening. So you're going to get your known solution. Just bring a small beaker in the stockroom. She'll give you the known solution. The known solution is going to contain ammonia. Well, we already tested for that, and so in this part we aren't testing for ammonium. We're testing for silver, lead, barium, manganese. There's also going to be some nitrate in there because all nitrates are soluble, so if we use nitrate salts, they'll all dissolve there. Okay, then we're going to add, in the first step, we're going to add HCl. So HCl, the reason for adding HCl is not the H+. Like, for example, ammonium doesn't want any more H+. We can't put any more on there. And so the HCl is not for the H+, the HCl is for the chloride. So we're trying metathesis reactions here. So we're going to add HCl as a source of chloride. And so ammonium plus chloride, do we get any reaction there? Precipitate? No, no reaction. Ammonium doesn't react, but silver and chloride, do we get a reaction there? Yeah. We're going to get a white precipitate of silver chloride, solid, white PPT. Lead. Do lead 2 ions like chloride? Yes. In fact, they like 2 chlorides, and they're going to form PbCl2, solid, which is PbCl2 is also a white precipitate. Barium and chloride. Barium and chloride precipitate? No, no reaction here. Manganese and chloride? No reaction here. Nitrate and chloride? No reaction. And so what we're going to have is we're going to have silver ions and lead ions precipitate. Now what we're trying to do in a precipitation is we're trying to separate, in the purpose of qualitative analysis, we're trying to separate out the ion from the other. And so what we want to do is how much HCl should you add? Well, let's see how much it says to add. It says to add 3 milliliters of HCl down here. Add 3 milliliters of 6M HCl. But you have to realize that that's just a guide, you know. It's just the suggested amount. It's like this. Let's say you're baking a cake, and it says to bake it for 25 minutes. And so you put it in there, and you go, okay, it's supposed to be in there for 25 minutes. But then you take a peek at it at 20 minutes, and it's starting to burn. It's starting to burn. You go, well, it said to leave it in there for 25 minutes, so you're going to leave it in there for 25 minutes, or you're going to take it out? You're going to take it out, right? You're going to have to make adjustments. Well, the same thing happens in chemistry. You know, sometimes we have to make adjustments depending on what we see is happening. And so this is why there's 2 types of chemistry students. There's the type that'll let it burn. Okay, it said 25 minutes. I'm going to follow the procedure exactly. I'm going to be a good student, and I'm going to let it cook and bake for 25 minutes. When they get their cake, it's like it's a black piece of carbon. Or you got those that will make adjustments and fine-tune things depending on what they're trying. The purpose is to try to make a good cake, and so they'll fine-tune the procedure. Well, what's the purpose of adding the HCl? The purpose of adding the HCl is to precipitate. We want to precipitate. Now, how much of it do we want to precipitate? Do we want to precipitate a little bit, or do we want to precipitate all of it? All of it. We want to precipitate 100% of it. All of it. We want to get all the precipitate we can get. And so what that means is this. That means you watch this. And let's say you start adding the HCl, and you're at a 0.5 milliliter of HCl. You're at a 0.5 milliliter, you have 2.5 milliliters to go. And it plateaus. There's no more precipitate forming. And so it's already reached a max, and then you're adding more. Another 0.5 milliliter, nothing happens. Another 0.5 milliliter, nothing happens. Should you add the rest, or should you say that's enough, it's done? You should say that's enough, it's done. Because if you keep adding and adding and adding when you don't need it, then we have to reverse that later on, which could screw up subsequent procedures. And so you gotta add enough to make sure you maximize the precipitate. there are other tricks too that happen, which you'll learn later on. But the situation is, let's say you get to 3 milliliters. This is the opposite scenario. You hit 3 milliliters and it hasn't stopped. You know, like if you go to 3.5, you get more. If you go to 4, you get more. It hasn't stopped. Are you going to be a good student and stop at 3 milliliters? No. In fact, that's not what we call a good student. A good student would recognize that, hey, I need to add more than what was prescribed. If it said 3 milliliters and I need more than that, let's say you're baking a cake and you do whatever the toothpick test, and it's already been 25 minutes. It says to bake it 25 minutes, but it's still raw in the center. Are you going to take it out? No, you're going to say, well, I better add some minutes to this, right? And so the same thing happens here. If it isn't completely precipitated, then it doesn't matter how much you add. You add enough until it's all precipitated, and you don't care how long that is. You know, you want to make sure it's cooked. You know, it's like food too. You don't want half frozen food and half cooked food. You want it fully cooked. So it doesn't matter how many minutes it takes to cook that frozen food, you want it fully cooked. And so this is the same mentality that we have for this. We make adjustments to fully cook things or do whatever we're trying to do. And so in this case, we're trying to precipitate. And so we're going to add what we want to do is we want to reach a plateau and then stop there. Okay, we don't want it to go down. You know, if it hits a plateau and starts going down, you better start. Maybe some side reactions occurring, so you better stop. So we want to maximize the precipitate. And so that 3 milliliters is just a guide. You would adjust it below or above depending on how the precipitation is going. But the problem is we got 2 white precipitates, so how can you tell the difference between silver chloride and lead chloride? They're both white. They're both cloudy white precipitates. You can't tell the difference. You can't. And so we need to get rid of one. And the situation is, how can we get rid of one? We're going to take advantage of a physical property of this. And that is solubility in hot water. In hot water, typically things are more soluble. Silver chloride is more soluble in hot water, and lead-2 chloride is more soluble in hot water. But it turns out that lead-2 chloride is dramatically more soluble in hot water. And so all we're going to do is we're going to heat this up. And so we're going to get 2 cloudy white precipitates, and then we're going to heat it up. We're going to heat it up in a what we call a hot water bath. Hot water baths take time to set up. And so this is the first thing you're going to do. Even before you start the ammonium test, you're going to make your hot water bath. Here. We'll put a burner there. And then we'll heat it up in the water bath. As you're heating it up in the water bath, you want to get your stir rod and try to crush up the crystals. If you crush up the crystals, that'll help them dissolve faster. And so what we're going to do is we're going to chop up the crystals here in hot water and get the lead to dissolve. The silver chloride should stay as a solid. The lead should dissolve when it's hot. And so PbCl2 will go aqueous. Well, how do you know you've dissolved all the lead? How you know is you just got to keep looking. If it looks like you've plateaued and no more lead, no more precipitate is dissolving, then it's probably done. You know? But if it looks like more and more of the cloudy white precipitate is disappearing, then you better keep going. You better keep going until you stop seeing anything change. This is critical here because we got to make sure we get rid of all the lead. And we're only left with the silver chloride as the precipitate. Okay, so this is what we're doing here. What we want to do is we want to separate the silver from everybody else and completely isolate it. And so what that means is we don't want any silver making it over here. We want to capture every single silver ion and bring it over here. And therefore, silver ion should be the limiting reagent, HCl should be the excess reagent. If silver ion, if we didn't capture all of it and silver ion gets, escapes and ends up here, it's going to screw up all these tests here. And you're going to get some very bizarre colors and very bizarre results. And so it's very critical that you do what we call complete separation. Okay, so we get the silver chloride over here, but how do we isolate it from the rest of the stuff? And the way we're going to isolate that is like this. We're going to filter it while it's hot. And so we're going to use our funnel and filter paper. There's filter paper in the back, and so with the filter paper you're just going to fold it in half, and then fold it in half again, and then just open up one end of it. So you'll have 3 sheets on one side, 1 sheet on the other. You put this in the funnel, and then just wet it down with a little bit of water so it sticks. Okay, then what we're going to do is we're going to filter that while it's hot. That is, while the lead, and so you got to be a little bit careful here, so that we trap the silver chloride as a precipitate here. And then what drains into your beaker, whatever you're capturing, test tube, is going to be lead, 2, barium, and manganese. And we also have ammonium and nitrate still present. Ammonium and nitrate. And excess HCl too. Okay, but I'll probably just focus on these 3 here. Let's just focus on these for right now. Okay, this is the precipitate. Oops, it's not AgCl2, it's Ag solid. It's supposed to be AgCl solid. This is AgCl solid is our precipitate. This solution, the liquid that's flowing through here, dripping into our beaker or test tube, this is called the filtrate or supernatant. So again, it's very important that we capture all the silver ions so that they're captured in silver chloride, in the form of silver chloride, and no silver ions make it through here. Likewise, it's important that our silver chloride is not contaminated, because our silver chloride, when we filter this, it's going to be wet with filtrate. Well, the filtrate's not pure. The filtrate has lead, barium, and manganese, as well as other stuff. And so this is what we call a dirty precipitate. It's dirty because it's got the filtrate solution or residue contaminating it. And so what we're going to do is this is typically what's done. We're going to clean up the silver chloride. There's 2 purposes in cleaning it up. The first one is not to lose any filtrate. And so what we're going to do is we're going to recover the little bit of filtrate that's soaking on the crystals here. Let's call our first wash. And so this is silver chloride wet with filtrate. And so we're going to wash with hot water. We're going to wash with hot water just a little bit because we don't want to lose, we don't want to lose the lead, barium, and manganese that's adhering to the surface of the silver chloride ions in the form of filtrate solution. And so we're going to wash that excess filtrate in here so that we don't lose those ions. But we don't want to wash too much, because if we wash too much, then it becomes too dilute and it becomes harder to detect. And so on the one hand, we're washing so we don't lose. We don't want to lose too much because this is a multi-step analysis. If at each step you lose, let's say I lose this much, I lose this much, I lose this much, by the end of this multi-step analysis, you might not have anything left. You might be testing and nothing happens because you've lost it all along the way. And so what we want to do is we want to just capture a little bit of the filtrate by washing. So our first wash, the purpose of this is to not lose any filtrate. And so I'm going to wash off the precipitate of the remaining filtrate back into the filtrate solution. Okay, the second wash, the purpose of the second wash is to clean off the silver chloride. And so the second wash, you could use a lot more water here, but we're going to change the beaker here and use a waste beaker. And so the second wash, the purpose of that is to clean the silver chloride, because we absolutely don't want any lead, barium, manganese or anything else coming and contaminating our crystals here, because the next step is to add sodium hydroxide. And hydroxide, not only does it like silver, it likes all those other ions as well, so it would screw up our results in the next step. So this is the waste. Now this should be clean silver chloride. We're going to get is clean silver chloride. Okay, we're going to leave the clean silver chloride in the filter paper and then just add sodium hydroxide to that. So if we have clean silver chloride here and then we add sodium hydroxide, and we keep the waste beaker under there, then we'll get a reaction. And the reaction is this. It's going to be silver chloride solid plus sodium hydroxide. This just looks like a double replacement reaction. What should form here? Silver hydroxide and sodium chloride. That's what should form. Silver hydroxide can decompose slightly, and so let me just go ahead and double this here to show you how it decomposes. 2 silver hydroxides can decompose into silver oxide. Silver oxide is more stable, and water, H2O liquid. And so the driving force for this is not precipitation, because we're getting rid of one precipitate to make another. This is what we call a solid-to-solid conversion. And so the driving force for a solid-to-solid conversion is the formation of a more stable solid from a less stable solid. And so it turns out that silver oxide is a much more stable solid than something like silver chloride, so we can get this reaction to occur. So it's a solid-to-solid conversion. Now let's say I wasn't successful. Let's say some lead, I wasn't successful in removing all my lead. And so let's say that this precipitate wasn't pure, clean silver chloride, but some lead 2 chloride precipitate were contaminating that. And so if I didn't get rid of all my lead, this is what would happen. Okay, I'd have my white PBT of lead 2 chloride, solid, and then I add my sodium hydroxide to this, and I end up with, well, what's going to happen is the white lead 2 chloride is going to get converted into white lead 2 hydroxide. Both of these are white. It turns out lead 2 hydroxide is more stable. So this is a white PBT. This is a white PBT. And so what's going to happen is white PBT is going to stay white. What we want is a white PBT being converted into a black PBT, a solid-to-solid conversion. Okay, if we see that white PBT turn into a black PBT, then we say that that is a positive test for silver ions in our original sample. And so if we get this black PBT, we have a positive test for silver ions. We should get a positive test for silver ions because our known standard will have all of them. Okay, let's move on here to the next step. Okay, assuming we got rid of all the silver over there, what we're going to be left with is lead, barium, and manganese ions in solution. And so how are we going to analyze that? Well, what's going to happen is, as this cools down, you can reprecipitate out the lead 2 chloride. You can heat it up again as well. Or you can a little bit of lead 2 chloride, PPT, is not going to affect the next step. Okay, so the next step is we have lead 2 ions, we got barium ions, and we got manganese 2 ions in solution, plus nitrate and ammonium. But nitrate and ammonium is pretty unreactive in metathesis reactions. Now we're going to add potassium iodide. It's not the potassium ions that are reacting, it's the iodide. So do lead ions like iodide ions? Chlorides, bromides, and iodides are all are all soluble except for silver, lead, and mercury. So yes, we're going to get PbI2. PbI2 solid is a yellow precipitate. Do barium ions like iodide? No, no reaction. Do manganese ions react with iodide? No, no reaction. Nitrate potentially could in a redox, but we'll talk about that later. And so in this step, we're going to get a yellow PPT of lead 2 iodide. Now, what's important is that we precipitate out all the lead. And how do we know we precipitated out all the lead? Well, how we know is we keep adding Ki until nothing happens, nothing changes. We just keep adding Ki. But the problem is this becomes so cloudy, you can't tell if anything's happening. It's like you're blinded by this intense, bright yellow cloud. And so what you're going to have to do is this. You're going to have to filter out the PbI2. Here. So we get our PbI2 precipitate, and then our filtrate. Our filtrate should be free of lead. Our filtrate should just be barium and manganese, plus the other stuff. But there shouldn't be any lead. And so how we're going to test this is, it was too cloudy, so if we filter out the PbI2, then we can test the filtrate, which should be clear. We're going to test this filtrate with some Ki. When we test the filtrate with Ki, if we see additional precipitation, that is, if we see any yellow cloudiness, then we're going to keep adding the Ki until it stops, or we can't tell anymore. And then we'll just repeat it. We're going to repeat it until we're sure we got all the lead out there. Okay, now for the PbI2 first wash only. The first wash only means we're just going to recover any filtrate that's adhering to the surface. We don't want to lose any barium and manganese ions, so we're just going to wash it just to recover the filtrate. No second wash. There's going to be no second wash here because do we need it clean? No, we don't need it clean because we're not doing anything with it afterwards. And so if it's a little bit dirty, it's fine. We just need a yellow PPT to confirm. So if we get a yellow PPT here, we've confirmed that we have lead 2 ions present in our original solution. Okay, now with the filtrate, we should be left with barium and manganese ions. So the next step is to separate out the barium from the manganese. It turns out it's not so hard to do with, what's this called? NaHSO4. Sodium NaHSO4. Anybody remember? Sodium bisulfate, yeah. It's sodium bisulfate or sodium hydrogen sulfate. And so what happens with bisulfate is going to act like sulfate in metathesis reactions. Can. And so something like barium likes sulfate. And so what barium's going to do is it's going to knock the hydrogen off there. And so barium reacts with the bisulfate, it's going to form barium sulfate, knock off the hydrogen as an H+. So we should get a white PPT here. However, manganese and sulfate don't precipitate. And so manganese with HSO4- gives us Nr. That's because sulfates are all soluble except for
lead, mercury, barium, strontium, and ammonium.
close. But I heard it over here. Calcium, strontium, and barium. And so we're good. This doesn't precipitate. And so what we should do here is we should add enough sodium bisulfate to completely precipitate out the barium. Now, how do you know all the barium's precipitated out? It should plateau. It should reach a peak. If you can't tell, then you should repeat this kind of procedure. Whenever you can't tell, if it's too cloudy, you got to filter it or let it settle. You know, if you wait like 15 minutes, then the cloudiness will settle down, and then you can test the clear liquid above the precipitate. Or if it's not settling down, you can filter it and then just test the filtrate with some additional precipitating agent. And so we'll just make sure that there's no more precipitate forming when we add the sodium bisulfate here. Okay, this one is only going to require the first wash. The first wash is to wash any residual filtrate back into the filtrate beaker. We don't want to lose any. This is not going to require any secondary wash because there's nothing else we do. We get a white precipitate here, then it's a positive test for barium in our original sample. So we get rid of the barium, and now all we should be left with is manganese and ammonium and nitrate, and other stuff that we might have in excess. So ammonium and nitrate present from the beginning. So if we just have manganese here, what we're going to do is we need to isolate the manganese from the other stuff. And the situation here is we don't want any ammonium getting through. And so we got to prevent the ammonium as well as the nitrate. Nitrates, nothing's really going to happen. And so what we're going to do is we're just going to add some hydroxide to this. If we add hydroxide, actually the hydroxide likes both. It likes manganese and ammonium. Ammonium reacts with hydroxide to form ammonia. So the hydroxide is going to kill off the ammonium. The ammonia should come off, or ammonia should stay in solution. But the hydroxide is going to also precipitate out the manganese. And so we end up with manganese 2 hydroxide solid. There. That's going to be it. That's our precipitate. Now, we're going to filter that precipitate out. We filtered that precipitate out. Now, what was the usual purpose of the first rinse? The first rinse was to yeah, the first rinse or the first wash was to make sure we didn't lose any filtrate. We wanted to make sure we capture all the filtrate and let it drain into the beaker. But our situation here is, what are we going to do with the filtrate? We're going to throw it away. And so you might go, well, then I don't need to wash it. Yes, you do need to wash it. We need to wash it. Because if there's ammonia contaminating our filtrate here, it's going to screw up the next step. And so we've got to make sure there's no ammonia contaminating, because when ammonia, which has been there from the beginning, reacts with hydroxide, we're going to form an aqueous ammonia solution, which can go gaseous as well. We don't want any. And so we need to wash thoroughly. Wash thoroughly. Okay, so then we should have some clean magnesium hydroxide precipitate. And so what we're going to do next is we're going to take this clean magnesium hydroxide precipitate and then dissolve it. We're going to dissolve it using nitric acid. This is just a double replacement or acid-base reaction. And what we're going to form is manganese 2 nitrate, which is aqueous, and 2 water. The driving force for this is stronger acid to weaker acid. And so what we're doing is we're dissolving the precipitate in acid. And then we're going to have manganese 2 nitrate. Manganese 2 nitrate is a strong electrolyte. And so it consists of manganese ions. And so what we're going to do is we're going to take that light brown precipitate, and the first step is to dissolve that precipitate with HNO3. Now, how much HNO3 do you need to add? You need to add enough to dissolve all the precipitate. That's it. And so it tells you to test with pH, but testing with pH is not necessary. Like, for example, here, it says to test it with pH. No, I wouldn't bother testing it with pH, because how much sodium hydroxide do you need to add? You need to add enough to plateau out, however much that takes. So it's not necessary to test with. The only reason we would test for we would test with litmus is because if nothing's happening. If nothing's happening, let's say you added 10 gallons. You're going, should I add 11 gallons? No. You added too much. Nothing's happening, so nothing's going to happen. And so the purpose of adding the litmus, doing the litmus test here, is in case you're getting no precipitate. The purpose of doing the litmus test here is we don't need to do that. We just need to add enough HNO3 to dissolve it. Once we get it dissolved, we have manganese 2. And then what we're going to do is we're going to take our manganese 2 and react it with sodium. This is called sodium bismutate. Sodium bismutate is consists of the sodium ion and the bismutate ion. The bismutate ion is BiO3. What's the charge on BiO3? Well, the charge on sodium ion is +1. Therefore, bismutate is -1. +1 -1. Now, there's a chemical property of bismutate that you should be aware of. Bismutate's not on our redox chart, but this is a very powerful oxidizer. And so what happens in this redox reaction is, if we take manganese 2+ and react it with bismutate and acid, what's going to happen is this. We're going to get permanganate. And so bismutate and acid can convert manganese 2 to permanganate. What do you know about permanganate? Tell me one chemical property of permanganate, like potassium permanganate. Permanganate is a very powerful oxidizer. We just talked about it yesterday. Permanganate is a very powerful oxidizer. It's quite dangerous. For this reaction to occur, Which one must be stronger, bismutate or permanganate? Bismutate is stronger. And so you got to watch out for this stuff. In fact, we're using solid sodium bismutate, which is located in that hood over there in the white plastic container. What you don't want to do is you don't want to spill any in your hands. It's a powerful oxidizer, so it'll oxidize your skin. You don't want to create a dust. It's very finely powdered. So you don't want to sneeze in there and create a dust cloud and inhale the dust cloud and get dust in your eyes and nose. It's going to cause you a lot of trouble because it is a very powerful oxidizer. And so what we're going to do is we're going to convert this. This is like very light pink lemonade to grape juice. And so we're going to go from a very light pink lemonade to grape juice. And this grape juice is, this is a purple solution. It's not a precipitate. We're not looking for any precipitates. This is aqueous, and this is aqueous. This is so faint, you know. It's more like a flavored water rather than a beverage. But you're looking for this grape juice, but don't drink. This is grape juice you shouldn't drink because it's a very powerful oxidizer. It's still a very powerful oxidizer. And so watch out for this reaction here. All right, so if we get the purple grape juice, then that's a positive test for manganese 2 in our original sample. Okay, we have two known standards. We have the cation standard, and then we have the anion standard. The cation standard had nitrate. You know, all the cations was nitrate. The anion standard, I think is in the back bench over there. The cation standard is at the stock room. The anion standard is going to contain chloride, sulfate, and nitrate. And these are going to be the sodium salts. You know, all sodium salts are soluble. So these are going to be the sodium chloride, sodium sulfate, and sodium nitrate in solution. We're going to be testing for chloride, sulfate, nitrate. We aren't going to be testing for sodium. And so let's do the first test. Now what we have to do is we have to get a fresh sample to test. And that fresh sample is 3 milliliters. And so we'll just get our anion, known standard, and we're going to do the chloride test here. The chloride test, we're just going to add silver nitrate. And so let's take a look. What happens to chloride, sulfate, and nitrate if I were to add silver nitrate? And so what's happening is I'm adding silver nitrate to supply silver ions. And I'm looking for metathesis reaction. So the first one is silver ions do like chloride ions, and we're going to precipitate out silver chloride, a white solid. Silver ions do like sulfate ions too, potentially, to precipitate out silver sulfate. However, this precipitate is fairly soluble. And so it's likely to be aqueous, not a PPT. And silver ions plus nitrate yields NR. And so this is going to be NR as well at this concentration. I know I told you sulfates. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Mercury, calcium, strontium, barium. But sulfates are all soluble except for silver, but silver should have an asterisk, you know, because it's like what we call slightly soluble, not totally soluble. Slightly soluble means it's fairly soluble. And so for the test for chloride is we get a white PPT. If we get a white PPT, then we must have silver chloride. If we have silver chloride, we must have had chloride in our solution to begin with. Okay, then we're going to move on to the sulfate test. The sulfate test, we're going to add barium nitrate here. The barium nitrate's supplying barium ions. This is from barium nitrate. Barium ions and chloride ions, do those precipitate? No, chloride only precipitates out with silver, lead, and mercury. And so we got no reaction here. Barium ions and sulfate ions, do those precipitate? Yes. We should get a white precipitate of barium sulfate. This is a white precipitate. Nitrate. Do barium ions and nitrate ions precipitate? No, there's no reaction here. So the only reaction is a white PBT of barium sulfate. That's a positive test that we had sulfate present in our unknown. And so we have to do this to a fresh sample. So silver nitrate we add to one test tube, and a fresh sample of anion mixture we add barium nitrate in another test tube. But what precipitates out with nitrate? So chloride, we got silver precipitate out. Sulfate, we got barium to precipitate out. But nitrate, what precipitates out with nitrate? Nothing. Because nitrates, acetates, and chlorates are all soluble. Nothing. So we aren't going to be able to use metathesis. What about acid-base? What do you know about the base strength of nitrate? It's so weak, it's pretty much neutral. And that leaves only what type of reaction? Redox. Well, that's okay because nitrate is pretty reactive in redox. What would you classify nitrate as? An oxidizer or reducer? Or both? Oxidizer? Yeah, nitrate's an oxidizer. Strong oxidizer, weak oxidizer? Nitrate is a strong? Well, it's in the middle, but did I show you the video of the Grand Camp? Do you guys remember the Grand Camp, Texas City? That was transporting ammonium nitrate? Or did I show you the China explosion?
Yeah,
The China explosion? Would you say that's in the middle? No. No, it's a strong oxidizer. Nitrate's a strong oxidizer, so we can take advantage of that property. What do we need for nitrate? We need H+, we need acid. And so the acid's going to come from H2SO4. It's going to supply acid. So nitrate plus 4H plus 3 electrons yields NO, gas, plus 2 water. That comes from the redox chart. So nitrate is, actually, you're right, it is kind of moderate, but it's still pretty powerful. And so nitrate is a strong oxidizer. Well, what is it going to oxidize? Well, it's not going to oxidize sulfuric acid. Sulfuric acid is a decent oxidizer itself. We're going to add something for it to oxidize. What we're going to add to it is iron 2 sulfate. In fact, we're going to add iron 2 sulfate to supply iron 2 ions. Iron 2 ions can be oxidized to iron 3 ions plus an electron. And so here's the redox reaction here. Except this is a bit tricky because we're going to use concentrated sulfuric acid. Now, you'll know when you spill nitric acid. When you spill nitric acid on your skin, do you know what color it changes to? Yellow. So if you have yellow spots on your skin, it's most likely nitric acid. If you spill concentrated sulfuric acid on your skin, do you know what color it turns? It turns charcoal because concentrated sulfuric acid causes third-degree burns, and it'll just basically charcoalize your skin. And so watch out. This stuff is nasty. And in fact, here's where you really want to pay attention to the rule. The safety rule AA. What does that mean? Add acids. Add acid. The reason is when you add acid, a lot of heat's generated. So you want to add acids to things, not things to acids. That way some of the heat can be dissipated. And so this is the way we're going to do it. We're going to have our nitrate in here. Then we're going to add our iron 2. And so we'll have our nitrate and iron 2 present already. And then we're going to add our acid. But you know, concentrated sulfuric acid is very nasty stuff. And so what we're going to do is we're going to have a special dispenser for the concentrated sulfuric acid. The special dispenser is called an auto dispenser. And the auto dispenser works like a syringe. There's a plunger. You can see it there. Do you see in the hood? Look at the glass jug. The thing that's stuck on the top of the jug is the auto dispenser. And we can set it. We can set it to 2 milliliters. And so what you're going to do is you're going to wiggle this up. You know, wiggle this up until it stops. That should be 2 milliliters. You've filled up the plunger. And then you're going to slowly depress this. As you slowly depress this, the concentrated sulfuric acid is going to drop in here. But you don't want to drop it straight into the solution. What you're going to do is you're going to tilt this at an angle. And you're not going to hold it with your fingers because wherever that concentrated sulfuric acid touches is going to get hot if there's moisture present. And so we're going to use a test tube clamp. And we're going to hold it via the clamp, not with our fingers. And you watch this stuff come out. This stuff looks like maple syrup. It's very viscous and dense. And this maple syrup, like concentrated sulfuric acid, will slowly sink to the bottom here. As it sinks to the bottom, it's going to form a layer of concentrated sulfuric acid on the bottom of this test tube. We don't want to mix it up. You know, eventually the sulfuric acid should dissolve in the water. But we want 2 layers. We want 2 layers because the reaction is going to happen at the interface between the viscous bottom layer and the less viscous top layer here. And that's where we're going to supply the H+. When we supply the H+, then the nitrate oxidizes the iron 2, getting converted to NO. Now, what we're going to have is we're going to have excess iron 2. We need excess here. So excess. Because when iron 2 gets oxidized to iron 3, iron 2 is green. Iron 3 is yellow. So if you look, there should be a green bottle over there. It's hard to see. But there's a green solution just to the right of this hood over here. That's iron 2. If you left the cap off that bottle, eventually it'll turn yellow. It'll become oxidized by air. But what we're going to do is we're going to put in excess iron 2. Do you know in your blood, in hemoglobin, what is it? Is it iron 2 or iron 3 in your blood? You know what it is? Iron 2 or iron 3 in your blood? It's iron 2 in your blood. And do you know what the iron 2 picks up? Oxygen. But it also picks up other gases. So for example, if there's carbon monoxide present, do you know your iron 2 in your blood would pick up the carbon monoxide as well? In fact, if there's carbon monoxide present, iron 2 likes carbon monoxide more than it likes oxygen, which means respiration stops. But anyway, the iron 2, you know what gas it also likes? It also likes NO gas. And so iron 2 is going to go from green, this is green, and when iron 2 picks up the NO, the nitrogen monoxide just gets stuck on there, like O2 gets stuck on there. And so now we have an NO molecule stuck on the iron 2, so this is the formula that it is. This is called a Lewis acid-base reaction. And this goes from green to brown. This is a brown solution. So what we're looking here for is, we are looking for a brown solution at the interface between the sulfuric acid and the green solution here. This should turn brown. Brown solution. We're not looking for a precipitate, but just a brown layer. Since this is a test tube and it's round, we call it the brown ring. We're looking for a brown ring. If we see the brown ring, then that means we must have had nitrate present in our original unknown. We got the brown ring. So first off, we're going to do all the tests on knowns. So the knowns are going to have everything in there. And so we should be able to observe everything that happens. Now, you have a choice. You could follow the observation report sheet like this. I don't particularly like that. I like to follow the observations like this. So I'd like to take the flow chart, maybe copy the flow chart into your notebook, and then just write about how much HCl you added. You know, what did the YPT look like? You know, any other descriptors in there. You can add your observations to the flow chart, which is my preference. Versus this, because when you add it to this, it's hard to know, you know, what is step 3? What is step 4, you know, visually. So here it's a lot easier to see visually what's happening. Okay, so first you're going to run the known. When you run the known standards, you're going to test positive for everything. Now the known standard, you can work with a partner. After you've gone through the knowns, then you're going to do an unknown. The unknown you're going to have to work individually. Not only that, I'm going to make it harder because for the known, you can use your lab manual and follow the procedure. For your unknown, you're going to have to use your observations and follow your observations. And so either the flow chart like this with your observations in there or this. But you have to have enough detail in there so you could repeat the experiment if you did it. Okay, and again, the unknown is going to be individual. And during your time with the known, you're welcome to ask questions. But when it comes to the unknown, you're on your own, pretty much. You have to, unless it's a safety-related issue. So think about that when you're doing your known. Make sure you understand each of the steps, where the chemicals are, and that type of stuff. There are some hazards in this lab. Silver, lead, barium are heavy metals. You know. Silver, lead, barium are heavy metals, so avoid contact. Silver ion is an oxidizer. It will turn things black. Watch out. Sodium hydroxide is an eye hazard. Nitric acid will stain your skin yellow. Concentrated sulfuric acid is a severe burn hazard. If you do spill any of the silver, lead, barium solution on you, make sure you wash for 15 minutes with soap and water. All right, are there any questions? Yes? No? Okay. I'm going to stop talking and then you guys can start the procedure.